Welcome to Spring LIB.
Alright everyone, so what we have here is a problem that will be solved that will be using Newton's second law and Hooke's law as well, because since we have a spring. So what we have block A, which has a mass of A, which is on top of a pan, B, which has a mass of B, and that's all attached to a spring that has a spring constant K, and that's attached to the bottom of the pan and to the ground. What we're asked to determine is the distance d that the spring should be compressed such that the separation of the block will take place when the spring becomes unstretched. So back to its unstretched distance. So as I said before, we're going to be using Newton's second law to solve this problem. So first thing we're going to do is find the equilibrium distance such that the spring is at equilibrium. And what we can say is first we can solve for the spring force at equilibrium and say that that's equal to Fs, which will be simply equal to the weights of the pan and the block on top. So that's going to be Ma plus Mb times G. Now just using Hooke's law, we can say that the y of equilibrium is equal to Fs over K, which is going to be equal to G over K, Ma plus Mb. Next, what we're going to do is we're going to assume that our block is now accelerating. So by drawing the free body diagram of our block, we can say that this is equal to MAY. And let's go ahead and draw our forces on the block. We have a normal force here coming from the pan, and we have the weight force of the block itself. So therefore we can see that the net force on this block is going to be equal to N minus MAG, which is equal to MAAY. We can go ahead and directly solve for this acceleration, and that's going to be equal to N minus MAG all over MA, which is equal to AY. Now what we're going to do is we're going to use this quantity but then also treat our block and pan as a single entity. So what we can do is draw the free body diagram of the block and the pan. So we have the pan, we have the block, we have the spring force that's acting in the positive y direction, and we have a weight force that's acting in the negative y direction. So by taking Newton's second law on this, we see that Newton's second law is in fact just equal to Fs minus the total weight, which is equal to the total acceleration, or total net force. And by plugging in for these quantities, we know that Fs is just going to be equal to K times YEQ plus D minus the total weight, which is Ma plus Mb times G, and that's equal to the total net force, which again is Ma plus Mb, but the acceleration is what we solved for in the previous step, and that's equal to N minus MAG all over Ma. Now recall that we're asked to find the point at which the block separates from the pan, so therefore our normal force at that time will be 0. So for n equals 0, we find that Kd is equal to negative Ma plus Mb times G, which gives us a d value, compression value, equal to negative Ma plus Mb times G over K. And that is our final answer.